Right. Welcome everyone to this Monash Cybersecurity Seminar. So today we are happy to welcome Shi-Feng Sun from Monash University. Dr. Sun was awarded his PhD degree in computer science and technology from Shanghai Jiaotong University in China. And after that, he worked as a research fellow in the cybersecurity group at Monash University, where he's a lecturer now in the Faculty of Information Technology. And his research interests are centered around cryptography and data privacy. And he's particularly interested in provably secure crypto systems against physical attacks, data privacy preserving technologies in the cloud storage, and privacy enhancing technologies for blockchain. And today he will talk about practical non-interactive searchable encryption with forward and backward privacy. So thank you, Shi-Feng. And the scene is yours.
Okay. Thanks for the nice introduction. I'm Shi-Feng Sun. Today I will give a talk on our recent work, practical non-interactive searchable encryption with forward and backward privacy. This is a joint work with Ron Stanfield, Shang-Qi Lai, Xingliang Yuan, Amin Saksad, Joseph Liu from Monash University, Xuan Nepo from DSSE 1, and Dao Gu from Shanghai Jiaotong University. In this talk, I will first briefly give a brief introduction to the background, and then briefly introduce our main contributions. After that, I will continue to introduce our main ideas and techniques, and then briefly introduce the performance of our solution. At last, I'll end this talk with a brief conclusion. With the explosive growth of data, more and more companies and individuals prefer to outsource their data to the storage service provider in recent years. There's no doubt that this kind of service brings us a lot of convenience. For example, we can access the data we want at any time and any place. Usually, in order to enable the server to operate on our data, for example, perform search for us, the data is uploaded in clear. Obviously, this will increase the risk of data breaches. To mitigate this risk and protect our sensitive data, a straightforward solution is to encrypt our data locally before outsourcing, and then upload the encrypted data to the server. However, this will seriously hinder the utility of the data. For example, the server will then be unable to perform search for us. So another question is that, is it possible for us to encrypt our data locally while enabling the server to search over the encrypted data? Sure, different methods have been proposed to accomplish this task. The existing solutions include the property-preserving encryption-based solution, fully homomorphic encryption-based solution. Also, we can achieve this goal by using oblivious RAM or symmetric searchable encryption. Among them, the property-preserving encryption-based solution is very efficient, but leaks much information. In contrast to the fully homomorphic encryption-based solution or ORM-based solution, leaks less information, but not practical. Different from the symmetric searchable encryption achieves a good trade-off between efficiency and security. This is what we focus in this talk. By the way, in this talk, we only focus on the symmetric searchable encryption with a single keyword search. So what is symmetric searchable encryption? usually we also call it searchable symmetric encryption. In general, symmetric searchable encryption involves two parties, a client and a server. When the client wants to outsource her files to the server, she first generates a file index and then encrypt the index and the files in some way. After that, she uploads the encrypted index and files to the server. Later, when the server wants to search the documents containing some keywords, say W1, she first generates a search token associated with these keywords and send the token to the server. With the token, the server can find out the corresponding documents matching this query, and then return the files, the documents to the client. To achieve efficiency, we usually allow symmetric searchable encryption to leak some information, but no more than the setup leakage and search leakage. Informally, the setup leakage refers to the total information leaked before executing any search, like the database size. For the search leakage, it usually consists of two kinds of information, the search pattern and the access pattern. The search pattern indicates whether a search query is repeated. And for the access pattern, it refers to the document identifiers and files that satisfy the search query. Up to this point, what I talked is made for a static symmetric searchable encryption. In practice, dynamic symmetric searchable encryption, DSSE for short, is usually more desirable. Except for supporting encrypted search, dynamic SSE also supports the update operations, which enable the client to insert a new document to the encrypted database or delete existing ones from it. The update operations enrich the functionality of SSE, but also introduce new leakage, new information leakage, namely the update leakage. Informally, it refers to the total information leaked during the updates, such as the total number of updates, or the types of updates, or even the updated documents or keywords. It has been demonstrated that such kind of information can be leveraged to break data query privacy. To capture the security of a dynamic SSE, the notion of forward and backward privacy was initialized by Stamford and others in 2014, and later formalized by Booth and others in 2017. Informally, the forward privacy ensures that the updates on keyword W cannot be related to the previous search queries on the same keywords. Suppose that to be more precise, we suppose that the client perform a sequence of operations. At time T1, she insert a document ID1 containing keywords W1. At time T2, she perform a search query on the keywords W1. After that, at time T3, she further insert a new document ID2 containing the same keywords W1. At this time, we hope that the server cannot establish the relations between the operations at time T2 and T3. In other words, the forward privacy ensures that the insertion operation during time T3 cannot be linked to the previous search at time T2. Until now, different methods have been proposed to achieve forward privacy, such as by using the trapdoor permutation or obliviated RAM and re-encryption. For backward privacy, informally, it guarantees that the updates and subsequent search queries should leak nothing about the deleted documents. More precisely, we suppose that the client at time T1 insert a document ID1 containing the keywords W1. At time T2, she inserts another document ID2 containing the same keywords W1. After that, at time T3, she decided to delete the documents ID1 containing the keywords W1. Finally, at time T4, she performed a search query on the keywords W1. Ideally for backward privacy, we hope that the search at time T4 reveals only the documents currently matching the queried keywords W1 and leaks nothing about the deleted documents ND1. But in fact, it is not easy to achieve this goal. This is because maybe it maybe still leaks some information about the deletions, like the deletion operation happens at time T3. According to the amount of information leaked during the updates, the backward privacy is classified into 3 types, from type 1 to type 3. We suppose that the current search is performed on the keyword W. The type 1 backward privacy allows to leak the documents currently matching the query W. The time steps of inserting these documents and the total number of updates on this queried keywords. And type 2 backward privacy additionally leaks the time steps of all the updates on these queried keywords. For the type 3 backward privacy, it further leaks which deletion cancels which insertion. Since the type 3, we can see that for the type 3 backward privacy, it is allowed to allow the most amount of information. So it is the weakest backward privacy. So far, there are many different approaches have been proposed to achieve backward privacy. Among them, the type 2 and type 1 schemes are usually designed by using expensive or complicated cryptographic primitives, such as ORAN, which usually involves multi-round trips. To the best of our knowledge, excluding by using SGX, the only way for designing a dynamic SSE within a single round trip is by utilizing the punctual encryption. So the question is how to design a practical, non-inductive, and strong backward private dynamic SSE without trusted execution environments. We answer this question formally and propose a new dynamic SSE scheme within a single round trip that can achieve the type 2 backward privacy. In more details, our contributions are as follows. We first propose a new cryptographic primitive named Symmetric revocable encryption and give a generic construction of this primitive from symmetric primitives. Then based on this symmetric revocable encryption, we propose the first practical non-inductive type 2 backward private dynamic SSE without relying on the trusted execution environments. Also, we implement our dynamic SSE in C++ and compare it with the state-of-the-art inductive and non-inductive SSE schemes in both LAN and WAN settings. Next, let me introduce our main ideas and techniques. Our starting point is the punctual encryption-based approach. Let's first recall this approach and take a close look at why this approach can only achieve type 3 backward privacy. Before going ahead, let's first briefly recall the main building block punctual encryption used in this approach. Punctual encryption consists of 4 polynomial time algorithms. The first is the key generation algorithm, which takes a security parameter and outputs a master secret key. The second algorithm is the encryption algorithm, which takes a message M and the associated tag, a set of tags T, and outputs the corresponding subtext CT. The third algorithm is the punctual algorithm, which takes as input the current punctured secret key SKA-1 and a new tag to be punctured TI prime. It outputs a new punctured secret key SKA. In contrast to SKA-1, SKA cannot decrypt the subtext encrypted and tag TI prime. So by repeatedly invoking this punctual algorithm, we can actually revoke the decryption capability of MSK over a set of subtext. The last algorithm is the decryption algorithm, which takes as input subtext generated and a set of text T, and punctured secret key SKA for text for the set of text R. It outputs the message M if no tag associated with the subtext has been punctured. Otherwise, the decryption fails. To apply punctured encryption to design a backward private SSE, we further require that the punctured encryption satisfy the so-called incremental puncture property. Briefly, this property ensures that this property means that each time we invoke the puncture algorithm, it will generate a new punctured key share. And this key share can be generated by only using a constant fraction of the previous punctured secret key. We call the punctured encryption satisfying this property incremental punctured encryption. Okay, now let's turn to the punctured encryption-based approach. The high-level idea of this approach is to use two forward instance, SSE instance, to achieve backward private dynamic SSE. In more details, to insert the document ID containing a keyword W, we first the client first generates an associated tag T, and then encrypt the document ID by using the punctured encryption and get the subtext CT. Then the client upload the subtext CT together with the corresponding tag T to the server by using the first SSE instance sigma add. When the client wants to delete a document ID containing keyword W, she first revokes the decryption capability of the current master secret key over the associated tag by invoking the incremental puncture algorithm. This algorithm will generate a new master secret key and a new punctured key share. Then the client will update the locally stored master secret key and upload the new punctured key share and together with the tag T to the server by using the second forward private SSE instance sigma delete. Later, when the client wants to search the document containing keywords W, she first generates the search token corresponding to the SSE instances sigma add and sigma delete, and then she sends the search token together with the locally stored master secret key share to the server. Then the server can use the search token to retrieve all the encrypted subtext, and the punctured key shares corresponding to the query. After that, the server can use the master key share MSK prime and together with the punctured punctured key shares to decrypt the retrieved self-test. If the underlying document ID is not deleted, then the server can successfully decrypt the self-test and retain the corresponding document identifier to the client. From this process, we can see that the server can learn when the deletion happens and which deletion removes which insertion. This is because the punctured key shares corresponds to the deletion operations. And so the server can keep track of the deletions through these punctured key shares outsourced to the server. This is why the punctured encryption-based approach can only achieve type 3 backward privacy. To achieve a high-level backward privacy, our basic idea is to make the deletions oblivious to the server by performing the deletions locally instead of incrementally outsourcing them to the server. With this idea in mind, a naive solution is to execute the punctured encryption-based approach in the following way. The insertion process is exactly the same as before. But when the client wants to delete a document containing a keyword, she first generates the associated tag and then record this tag locally. Later, when the client wants to perform a search query, she first generated the search token as before, and then generated the punctured secret key for all the recorded tags corresponding to the queried keywords by repeatedly running the puncture algorithm. Then the client sends the search token and the punctured secret key to the server. With the token, the server retrieve all the self-tests containing the queried keywords. And then the server uses the punctured secret key to decrypt all the self-tests and retain the non-deleted documents to the client. Under this framework, we can see that the server gets nothing about the deletions because the deletions are performed locally. However, this naive solution suffers from two drawbacks. The first drawback is that the client needs to record all the tags to be deleted. So this will incur a large client storage request. And the second drawback is that the size of the punctured secret key scales linearly with the number of deletions. So this will incur a large search communication cost. To overcome these two drawbacks, we introduce a new technique called compressed symmetric revocable encryption. Roughly speaking, it is an encryption scheme that enables us to revoke a list of tags in one shot with a low storage request. More precisely, symmetric revocable encryption consists of 4 polynomial time algorithms. The first algorithm is a key generation algorithm, which takes the security parameter and outputs a master secret key. And the second is the encryption algorithm, which takes the master secret key and a message and the associated tags T with this message. It outputs a self-test for this message. The third algorithm is the key revocation algorithm, which takes as input the master secret key and a set of tags to be revoked. It outputs a revoked secret key SKR for the revocation list R. The last algorithm is the decryption algorithm, which takes as input the self-test associated with the set of tags T and the revoked secret key SKR for the revocation list R. It outputs the message if no tag associated with the self-test belongs to the revocation list. Otherwise, the decryption will fail. For the compressed SIE scheme, we miss that for the key revocation algorithm, when we use this algorithm to generate a revoked secret key, it only requires a low storage. Also, we give a concrete construction of compressed SRE based on a Bloom filter and multipuncture PIF. Before presenting our concrete construction, I first briefly recall the notion of a Bloom filter and a multipuncture PIF. For the Bloom filter, briefly, it is a probabilistic data structure which can be used to represent a set of elements with a low storage request. A Bloom filter parameterized by M and K consists of two components, H and B. B is M bit array, and H is a collection of independent hash functions. Each mapping the set of elements S to the indexes of the Bloom filter. The Bloom filter supports two operations, insert and check. Let's take the 16.3 Bloom filter as an example. To insert an element of S, say T1, to the Bloom filter, we first compute the values of these hash functions at T1, and then we set the value of the entries indexed by these hash values to be 1. Similarly, we can insert all the other elements in the set to this Bloom filter. To check if element T belongs to the set S, we first compute the corresponding hash values to this tag to this element T. Then we check if the value of the entry indexed by each hash value is 1. If not, it is believed that the element T is not an element of S. Otherwise, T belongs to a set S with a large probability. For a multipuncture PIF, exactly for T puncture PIF, it is a standard. It is similar to a standard PIF, except that it additionally includes two algorithms: the multipuncture algorithm and the evaluation algorithm. Taking as input PIF key and a set of elements, L elements. L is not larger than T. Then the puncture algorithm can generate a punctured secret key, KS. With this punctured key, we can evaluate the PIF value at any point not belonging to S by using the evaluation algorithm. For our application, we only need a weak security, which only allows the adversary to ask for a single punctured key query. This security ensures that even given the punctured secret key for S, the PIF values at these points are still pseudo-random from the point of the adversary's view. Now let's see how to use these two building blocks to construct the CSRE. For the key generation algorithm, it takes a security parameter and the Bloom filter parameters HB. It outputs a PIF key and an empty Bloom filter H and B. For the encryption algorithm, when we want to encrypt a message associated with tag T, we first compute the hash value. We compute the values of the hash functions at tag T. Then we evaluate the PRF values at these hash values. After that, we use these PRF values to use these PRF values as a symmetric key to encrypt the message M. Here, the SE is the standard symmetric encryption. For the key revocation algorithm, when we want to generate a secret key for the revocation list R, we first insert all the tags in R to the Bloom filter. And then we will generate the revoked secret key based on this Bloom filter. In particularly, we will generate the punctured secret key. We will use the puncture algorithm of the multi-puncture PRF to generate the puncture secret key for the indexes of the entries of the Bloom filter with value 1. According to the properties of the multi-puncture PRF, with the puncture secret key, we can compute the PRF values at the index of the entry with value 0. For the decryption algorithm, we want to decrypt the self-test generated on tag T. We first check if tag T belongs to the revocation list R. Particularly, we will compute the hash value corresponding to the hash value at point T. If the tag T does not belong to the revocation list R, then there must be at least one entry with value 0. Then we can use the revoked secret key to compute the PRF value at the index of this entry. After that, we can use the PRF value to recover the message. We also show that our construction can satisfy the semantic security. Briefly, to show the security, our idea is to split the PRF keys corresponding to the indexes of the Bloom filter into 2 parts. One part corresponding to the challenge tag, and the other part corresponding to corresponding to corresponds to the other indexes. After that, we can change the PRF values corresponding to the channel tag T star to pseudo-random values, random values based on the security of multi-puncture PRF. After that, we can change the self-test to the encryption of constant messages. We can reduce this the indistinguishability of these 2 parts to the security of symmetric encryption by a hybrid argument. Based on this new CSIE scheme, we propose our type 2 backward private SSE Aura. Except for using CSIE, we also need a forward private SSE instance. In more details, when the clients want to insert a document containing QoS, she first generate an associated tag and use the CSIE scheme to encrypt the document ID and get the self-test CT. Then the client uploads the self-test CT together with the tag to the server by utilizing the SSE instance sigma-add. For the deletions, when the client to delete the documents, continual keywords, WC first generate an associated tag, and then insert this tag to the Bloom filter. Later, when the client wants to perform a search query over keyword WC first generate the search token corresponding to the SSA instance sigma, and then generate the revoked secret key based on the compressed data structure of Bloom filter. And then she send the search token and the revoked secret key to the server. Then the server uses the search token to retrieve the self-test containing the queried keywords. After that, she uses the revoked secret key to decrypt the self-test and retains the non-deleted documents to the client. And this, as we mentioned, under this framework, the server can get nothing about the deletions. So our dynamic SSE scheme Aura can achieve a high level backward privacy. Okay, next, I briefly introduce the performance of our construction. To compare with the state-of-the-art dynamic SSE scheme, including the latest time to backward private SSE scheme SDD and the latest non-interactive dynamic SSE scheme Genus++, we implement our SSE scheme Aura with C++ and use Swift as the network framework to test the delay from the framework. We evaluated the performance of our solution in both line setting and WAN settings. The evaluation results demonstrate that in terms of the search time, in the line setting, our scheme Aura is at most 3 times slower than SDD. But in the WAN setting, SDD is about 11 times slower than our solution Aura. We also compared with Genus++. The results show that our scheme is much faster than Genus++, especially for the large number of deletions. We also compare the insertion time cost and the deletion time cost, both of which are much faster than the previous schemes. And last, I have to say that to achieve type 2 backward privacy, actually Aura occupies more client storage space than SDD. Because SDD, the client storage cost of DD is 0.1. But fortunately, this cost is moderate for modern devices. Okay, and last, I briefly conclude this talk. In this work, we propose a practical and non-interactive dynamic SSE, which can achieve type 2 backward privacy without hardware assumptions. To achieve this goal, we propose a new cryptographic primitive, namely a symmetric revocable encryption, and also present a generic construction from Bloom filter and multipuncture PIF. It is still challenging to design a practical type 1 backward privacy dynamic SSE. The source code of our scheme is available at GitHub. Okay, that's it. Thanks for your attention. Any questions?
Thank you, Shi-Feng, for the talk. Do we have any questions, anyone? If you have questions from the audience, you can type it in the Q&A. Or if you're in the panelist, you can unmute yourself. I think I can make a start. Could you go back to the slide where you had the runtime comparison, the search time comparison, where Aura was faster than This CDD, SDD one, sorry.
Okay. This one?
Yeah, this one. But this one, so it says search time.
Okay, this one is Aura is slower than STD. Technically, yeah, what you mean is the comparison in one setting, right?
Yeah, the other one should be slower, right?
Yeah. This is because actually STD is interactive scheme. So we also compare it with in the last setting. In the last setting, actually, this only compares the computation cost. I mean the first time.
So STD is, we are saying it's faster, right?
Yeah. In this case,
Okay.
Yeah.
Sorry. I think I misunderstood. I thought you were saying Aura was faster. Okay.
Yeah. But in one setting, I mean, because Aura is non-interactive, so we want to emphasize that the non-interaction is better than the interaction.
Okay.
Non-interactive is better than interactive as the SSE.
Yeah, I see.
Yeah, but in this case, our evaluation results shows that our scheme is much faster than STD because it is interactive, so it is affected by the communication condition, right?
Yeah. Cool. Any other questions?
Maybe I ask next question. Shi-Feng, speaking, yeah. So Shi-Feng, is there any other difference between SDD and Aurora in terms of functionality rather than interaction? Like, for example, I believe Aurora was only supporting single keyword search, right?
Yeah.
I think SDD is supporting multiple keyword search, right?
No. STD also supports only single keyword search, but STD, just as I mentioned, STD enjoys small client storage. This client storage is only 1, but for our solution, the client storage is a bit larger. But because we ask the client to do deletions locally, right? So we achieve the high level backward privacy at the cost of a bit higher client storage.
Yes, thank you.
Any other questions? Shujie, do you have a question? Okay, I guess we don't have any more questions. So thank you very much.
Hi.
Now we can hear you. Yeah.
Oh, okay, sorry.
Yeah,
I have one question about the Bloom filter. So the Bloom filter storage is on the client side, right?
Yeah.
So with more hash functions, the storage overhead on the client will be larger, right? So my question is, what's the benefits of using more hash functions for the Bloom filter?
Thanks for the question.
I think this relates to this parameter K, right? I was also wondering.
Yeah. This is about the parameter K. Actually, there is a relation between the number of elements inserted to the Bloom filter and the number of hash functions and the size of the Bloom filter. I think Yeah, maybe when we use more hash functions, yeah, when we use more hash function, I think we can improve the decryption time, because you use more hash functions, you will revoke the punctual secret key on more leaves, on more indexes of the Bloom filter, right? Yeah, in this case, you only need to you only need to compute the in our instantiation. We actually instantiation the multi-puncture graph with GGM tree. In this case, you only need to compute less PRGs on the GGM tree.
I see.
Yeah, I think it is about it is related to the decryption time.
So more hash functions and more efficient for the decryption, I guess.
Yeah, it is like this. Yeah.
Okay, thank you.
Yeah, this is also why you can see that we give two set parameters for h equals 5 and h equals what I don't remember. Yeah, two settings, right? Actually, they have a trade-off between the client storage and the decryption time.
Okay.
Yeah, hopefully I answer your questions.
Yeah. Okay. Yeah, thank you.
I think we also have a question from the audience. Yunling, you should be able to ask your question now.
Yeah. Hello.
Yeah, we can hear you.
Yeah. I have a little question that the key revocation algorithm is performed in the by the data owner, and can we move this algorithm to the cloud computing?
No, I think because the key verification algorithm is performed by the data owner, right? So
yes.
Yeah. I think finally you can ask the server to do it for you, because after the search we need to change a new master secret key under this framework. So in this case, even you finally give the master secret key to the server and ask the server to generate the revoked secret key for you, it doesn't affect the security. Yeah, I think maybe we can ask the server to do this for the data owner, because the revoked secret key actually is generated just before the search operation, right? So yeah, I think it doesn't affect the security, even we do it like this.
Does this answer your question? I guess so. So if we do not have any further questions, thank you very much everyone for tuning in, and thank you Shi-Feng for the very interesting talk, and I hope to see you all in the next seminar. Thank you everyone. Bye.
Thank you.